This is the first of three notes that you're going to be taking for our last unit, which is Unit 12 on differential equations. Before you go any further, I would suggest you pause the video and take a little bit of time just to read that portion. And having read that portion, another way to say all of this is that we're talking differential equations as a set of problems where we're going to give you a slope or an equation for finding the slope, and then we're going to ask you to find the equation that came from. We can think about this as, if this is the slope, what was the parent equation for this? Well, another way to say that is, if this is the equation that gives us the slopes, what's the antiderivative? So for this one, it's pretty straightforward. The antiderivative is going to be an x squared function, and then you just have to make sure that the coefficients balance out, and with a little bit of thinking, you can see that the antiderivative here is going to be 1/4 x squared, and then we don't know how high it is on the y-axis, so we have a plus c that gets added in. So we're going to start with this equation. We already know what the antiderivative looks like, but we're going to walk through next couple examples here, walk through the techniques that we would use to find this if we didn't have an easy equation like this one to work with. So the first technique is drawing something which is called a slope field. And the way that we're going to do this is we take this equation for the derivative right here, and then we're going to plug in different values of x and figure out what the slope will be. So for example, we can start with, let's start and say if x was equal to -3, well then it's pretty straightforward that the slope would be equal to -3/2, right? Which means that along this set of locations on our graph, the slope is always going to be -3/2. And what I'm going to do here is I'm going to draw in teeny little segments here that represent slopes of -3/2. And apologize if my accuracy is a tad bit off. They should all be parallel. Please imagine that they are parallel for my sake, actually for your sake, right? So this is all of the, along the part of the graph where x is equal to 3, we have all of these slopes, and for each one of these slopes, right, m is equal to -3/2. Over here on this side, same thing is going to happen, except instead of the slope being -3/2, the slope is going to be +3/2. And then we're going to get these slopes that look like this. And again, I'll mark this for us. So right here, anything in this vertical strip is going to have a slope of +3/2, right? And then we're going to do the same thing for -2, for -1, for 0, for +1, and for +2. And with the beauty of technology and pause buttons here, I should be able to pause this and then come back with the slope field all drawn. Okay, so there's our slope field, and notice what I've done is I've gone through and I plugged in an x equals -2, figured out what the slope is at -2, and then at all of the places where x is equal to -2, I've sort of sketched out what the slope would look like there. And I'm choosing to do this at the sort of at even increments. I could just kind of fill in the whole thing, but then it would not be terribly helpful visually. All right, so again, this in here is what we refer to as a slope field. Now what the slope field allows us to do is it allows us to do something like problem B here, which is we're going to take and roughly sketch out the solution when our function has an x value of 0 and has a y value of 1. So that means that it would be right here. So if we know our function exists here, well then when we go off to the left, as we start off to the left, we start off with a slope of 0. By the time we get over into here, into this column, our slope is going to be at 1/2, and then when we continue further along, our slope is going to be at 1, and when you can continue even further along in the x direction and get over to this column, our slope is going to be at 3/2. And if I can do this kind of smoothly, then we get something that looks like that. And then on the other side, it's going to be symmetrical and do sort of the same thing like that. Clearly a parabola. My drawing is not as clear as it could be, but you get the idea. For this problem, problem C, which we'll do in purple, we're going to start now when we plug in a value of 3 for x. So that puts us over here. We're going to get a value of 1 for y. So we're going to be right here. And if we follow the slope field, we're going to go from this point where x is equal to 3, and we're going to head left. And when we do that, we're going to start with a slope of 3/2, and then as we slide over here, we end up with a slope of 1, and as we come further down and over in here, we end up with a slope of 1/2, and by the time we get over here to the y-axis, we have a slope of 0, and then we come back following the slope field, and we end up like this. Right, so the slope field is kind of pushing our function in the direction that it's supposed to be in. All right, and finally, the last way that we can think about this is we can do it algebraically. And again, we've been given a slope. We know that the slope follows this pattern 1/2 x. We are given a point here. Basically, this is the point where x is equal to 3 and our y value is 1. So if we know that this is the slope, and we know that we have this point, right? We up above here, we had already determined that the antiderivative of this was y is equal to 1/4 x squared plus c. You see it there in blue. Well, if I know that I have this point 3,1, then I can algebraically solve this, because I know that my parent function, which is always going to have a slope of 1/2 x, my parent function looks like this. It's 1/4 x squared plus c. I have a value for x and y, so I can plug those in. So I know that the y value is 1, and this is 1/4 times the x value. The x value is 3. I square that, and we add c to that, and then I have one equation with one unknown, and I can solve this. This is going to be 9/4 here. I subtract 9/4 from both sides, and we're going to end up with c is equal to -5/4. So algebraically, the equation that I'm looking for here in D is y is equal to 1/4 x squared plus -5/4.